When it comes to nuclear weapons, there is really no good place to detonate one. They are dangerous under any circumstances. However, among all the terrible locations where a nuclear explosion could occur, outer space may be one of the worst. At first glance, that sounds surprising. Space is mostly empty and far away from human civilization. So what harm could a nuclear explosion there possibly cause? During the Cold War, the United States decided to find out, and the results were far more dramatic than anyone expected. In the late 1950s and early 1960s, tensions between the United States and the Soviet Union were at their peak. The space race was underway. Nuclear arsenals were growing rapidly, and military planners were searching for new strategic advantages. Some scientists and military officials believed that detonating nuclear weapons high above Earth could provide both defensive and offensive benefits. One of the main ideas involved the electromagnetic pulse, or EMP, produced by a nuclear explosion. An EMP is a burst of electromagnetic energy capable of damaging or destroying electronic systems. Since intercontinental ballistic missiles travel through space during part of their flight, military planners theorized that a high-altitude nuclear explosion could create a powerful electromagnetic shield. Any enemy missile passing through that region might suffer electronic failures, preventing it from reaching its target. At the same time, scientists were learning more about Earth's magnetic field. Generated by the movement of molten metal within Earth's core, this magnetic field extends far into space and forms a protective shield around the planet. It traps many of the charged particles arriving from the sun and helps make life on Earth possible. Researchers realized that a thermonuclear explosion inside this magnetic environment would release enormous numbers of highly charged particles. Instead of simply dispersing into space, many of these particles would become trapped by Earth's magnetic field and travel along its magnetic lines. In theory, a carefully placed nuclear explosion could send electromagnetic disturbances over vast distances, potentially disabling enemy radar systems, communications networks, or missile defenses. To test these ideas, the United States launched a series of nuclear experiments in the Pacific Ocean. In 1958, Operation Hardtack included 35 nuclear tests, 3 of which were conducted at high altitudes. The first of these experiments was called Yucca. A relatively small nuclear device was attached to a giant balloon and lifted to approximately 85,000 feet above Earth. After the detonation, scientists measured the resulting EMP and discovered something remarkable. A high-altitude nuclear explosion could generate an electromagnetic pulse more than 1,000 times stronger than a similar explosion at ground level. For military planners, this result was extremely significant. It suggested that EMP effects could become a powerful strategic weapon. The next experiment, known as TEAK, used a much larger nuclear device carried by a Redstone missile. The weapon was intended to explode high above the Pacific Ocean. However, due to guidance problems, it detonated almost directly above Johnston Island. Witnesses described the blast as creating a miniature sun in the sky. The flash was visible hundreds of miles away and lingered for an extended period. The effects were startling. Thermal radiation from the explosion was strong enough to cause sunburns among personnel on the island. Communication systems across large areas of the Pacific experienced significant disruptions for hours. The test demonstrated that high-altitude nuclear detonations could affect regions far beyond the immediate blast zone. A third experiment, called Orange, was conducted at a lower altitude. While still impressive, its effects were noticeably weaker than those of TEAK. This helped confirm an important conclusion. The higher the altitude of the detonation, the greater the electromagnetic and atmospheric consequences. Despite these findings, many questions remained unanswered. Several years later, the United States launched a new series of experiments known as Operation Fishbowl. Conducted in 1962, the same year as the Cuban Missile Crisis, Fishbowl aimed to study the interaction between nuclear explosions, Earth's magnetic field, radio communications, and high-altitude EMP effects. The project involved cooperation among the military, the Atomic Energy Commission, and several scientific organizations. Monitoring stations were established across the Pacific and in the Samoan Islands. scientists hoped to observe how charged particles released by a nuclear explosion would travel along magnetic field lines between the northern and southern hemispheres. The early stages of Operation Fishbowl were plagued by failures. The first planned test, Bluegill, ended when the missile carrying the nuclear warhead went off course. Engineers destroyed the missile before it could continue its flight. Fortunately, the warhead remained in safe mode and did not explode. A second attempt, called Starfish, also failed. The missile suffered a malfunction shortly after launch, broke apart, and scattered plutonium-contaminated debris over Johnston Island and the surrounding ocean. Despite these setbacks, the program continued. On July 9, 1962, the United States carried out one of the most famous and consequential nuclear tests in history, Starfish Prime. A Thor missile successfully carried a 1.4 megaton thermonuclear warhead to an altitude of approximately 400 kilometers, or 250 miles above Earth. This placed the detonation well within the near-space environment. Starfish Prime remains the largest nuclear explosion ever conducted in outer space. The appearance of the explosion was unlike the classic mushroom cloud associated with nuclear weapons. In space, there is no atmosphere dense enough to produce such a cloud. There is also no oxygen to sustain fire. Instead, observers saw an intensely bright sphere of light expanding outward in all directions. As it grew, the edges developed strange tendrils and glowing patterns, creating a scene that many described as both beautiful and unsettling. The visual spectacle, however, was only part of the story. The electromagnetic pulse generated by Starfish Prime was far stronger than scientists had predicted. In fact, many of the instruments designed to measure the EMP were overwhelmed and driven beyond their maximum limits. Researchers could not determine the exact strength because the pulse exceeded the measuring capabilities of their equipment. The effects reached far beyond the test site. In Hawaii, roughly 1,400 kilometers away, electrical systems experienced disruptions. Streetlights failed, burglar alarms were triggered, and telephone communications suffered damage. The explosion demonstrated that a high-altitude nuclear detonation could affect infrastructure over enormous distances. Another dramatic consequence was the appearance of artificial auroras. Brilliant glowing lights spread across the Pacific sky, stretching along Earth's magnetic field lines. Similar auroral displays appeared in the southern hemisphere, confirming that charged particles from the explosion had traveled vast distances through the planet's magnetic environment. Perhaps the most important discovery involved Earth's radiation belts. The explosion injected huge numbers of high-energy electrons into near-Earth space. These particles became trapped by Earth's magnetic field, creating an artificial radiation belt around the planet. Radiation levels in low Earth orbit increased dramatically. The consequences for satellites were severe. Within days, several satellites stopped functioning. Others gradually failed over the following months as radiation damaged their solar panels and electronic systems. In 1962, there were relatively few satellites in orbit, yet the effects were still substantial. Researchers later reported that some of the radiation produced by Starfish Prime remained trapped around Earth for as long as 5 years. The experiment provided invaluable scientific data, but it also revealed how vulnerable space-based technology could be to nuclear activity. The following year, in 1963, the United States and the Soviet Union signed the Partial Test Ban Treaty, which prohibited nuclear testing in the atmosphere, underwater, and in outer space. This agreement effectively ended the era of large-scale, high-altitude nuclear testing by the superpowers. Looking back, Starfish Prime was not even among the most powerful nuclear weapons ever built. During the Cold War, bombs existed that were 10, 20, or even 30 times more powerful. The realization of what such weapons might do in space remains deeply unsettling. Today, the risks would be far greater than they were in the 1960s. At the time of Starfish Prime, only a handful of satellites orbited Earth. Today, thousands of satellites support global communications, navigation, weather forecasting, financial systems, military operations, and internet services. A similar nuclear detonation in space could expose many of these satellites to intense radiation and electromagnetic effects. The resulting damage might not simply destroy individual spacecraft. It could create widespread instability throughout Earth's orbital environment. Damaged satellites and debris could collide with one another, producing even more debris in a cascading chain reaction. Such a scenario could make large portions of Earth's orbit unusable for years or even decades. Meanwhile, the EMP generated by a high-altitude nuclear explosion could threaten electrical grids, communication systems, and electronic infrastructure on the ground. Massive technological disruption, without a single city being directly targeted by the blast itself. In the end, The history of nuclear testing in space revealed something extraordinary. Scientists learned that Earth's magnetic field can carry the effects of a nuclear explosion across immense distances, that satellites are highly vulnerable to radiation, and that EMPs can have consequences far beyond what early researchers imagined. The experiments were scientifically fascinating and visually spectacular, but they also demonstrated just how dangerous nuclear weapons can be when combined with the complex environment of space. The lessons learned from Starfish Prime and related tests remain relevant today, serving as a reminder that some technological capabilities are so destructive that they are best left unused.